This meeting is being recorded.
So the next additional aspect of aqueous equilibria that we're going to take a look at here is something referred to as buffers. So buffers are solutions that are a combination of a weak acid and base that are the conjugate acid and base pairs. So we have these weak acid and base pairs, and what happens is they're actually pretty resistant to changes in pH, even when you add a strong acid or a strong base to your system. So we're going to take a look at an example of a buffer solution or a buffer system below here. So we have our weak acid, we have our HF, and then we have fluoride ions. So we're given a scenario over here where a source of those fluoride ions is provided here with this sodium fluoride, and we have equimolar, so we have equal molarities of equal concentrations per the same volume, right, of our HF and our F negative. So because of that, we've created this buffer system, and then we're told when we react this system with hydroxide ions. So let's see here, we'll go down to our image below. We see our buffer system here in the middle with our equimolar amounts of HF and F. We add hydroxide. We can see in this equation below, what happens is the strong base here reacts with my weak acid to increase the weak base concentration. So again, we're adding strong base, our hydroxide, so that's my SB in this equation here. My weak acid that's already in my buffer, HF, reacts with that, and we get a production over here that we see of weak base. So a similar shift would happen if I added acid to my buffer system. So here we go. I'm going to add, hydrochloric acid or some source of H+. I'm going to have a shift in the other direction then. So now my base, my fluoride ion, my weak base in my buffer system will react with my strong acid, and I'm going to have a shift to produce more weak acid, and that's what we see here. So as mentioned previously, when you put a stressor on a system, the Le Chatelier principle applies, and we'll see a shift to reestablish equilibrium. So that's what this buffer system is really good at doing. It's good at consuming hydroxide or hydronium ions and kind of rebalancing things out so the pH barely changes. So there'll be some slight indication of change, but not a drastic change as we would normally see without a buffer in place. So whenever we have to do buffer calculations, we're going to use something called the Henderson-Hasselbalch equation. So the name is given down below. So we can actually derive, if you'd like to stay tuned for a minute, the Henderson-Hasselbalch equation from the general acid ionization equation. So by that I mean, if we just have this generalized equation, so we add any old weak acid to water, we're going to always produce hydronium and the anion. So our Ka expression would look like this, right? We have our products on top. We have our weak acid, our reactant on the bottom. We exclude water, as always, from the equation. Now what we're going to do is, as we derive this, we're going to take this equation and we're going to take the negative log of this side, and I'm also going to take the negative log over here. So that applies to all of these components, etc., etc. Then we're going to rearrange this equation so that we have negative log of Ka is going to be equal to, right, the negative log of, I'm going to take this out here. So the negative log of negative A over HA will be one entity, but I'm going to put this here, the negative log of my hydronium on top, and then next to that, I'm going to say plus the negative log of, so this will be, again, this combo A negative over HA. And for those of you that know the Henderson-Hasselbalch equation, you might already see it forming here. What we're going to have will look like this. In the end, we're going to have pKa over here. This is pH, we know that. This we can say is just minus the log, right? Plus or minus, so minus the log of our base, right? Concentration over our acid. So this is still a pretty unclear form of this equation. So I'm going to rearrange it actually one more time, because usually we're solving for pH. And this is the most appropriate form. So we're going to say pH in this rearranged equation is going to be equal to pKa. I just divided and multiplied each side accordingly. Added and subtracted each side accordingly. And then we have minus the log of our base over acid. So this is the derivation of the Henderson-Hasselbalch equation given here. So again, this form is for weak acids. There's another formula that we're not going to use, but it applies to weak bases that utilizes pKb. This is the equation we'll use in the next couple sample exercises.